The following audio recording has been designed for learning purposes only. Do not share, distribute, or provide any type of copies, or this audio lesson will not be made available to you. Good luck with today's lesson.
Squared minus 4a1, and then c is minus 6.8 times 10 to the minus 7. Just as an aside, this is positive, so that means the whole thing under the radical sign is positive, so there's no chance of an imaginary term. There shouldn't be, but if you made a mistake, that would tell you immediately that there's some problem if you come up with the square root of -1 in there somewhere. Okay. And, all right, so I'm just going to do all of this out at once. So 6.8 times 10 to the minus 4 squared. And then then we have 4 times 6.8. And then plus, okay, so this comes up to be 3.18 times 10 to the minus 6. I'll do it one more time here just to be careful. So 4 times 6.8 plus recall. Right, okay. And that's all over 2. And so that's going to be 2 possibilities. It's going to be, let me just finish this up. .18, there we go. Okay, and then we have 0. I'll do it this way. Too many zeros. Okay, so which one, plus or minus, which one can we automatically get rid of? This is how it usually plays out. This is negative. So the negative one, we can't subtract off that negative one, and we end up with a negative number. So really our only choice is going to be that. That has to be the correct one. If that one comes up -2, then there's some problem. But we can't use the negative term because it'll just give 2 negative terms, and our concentration will be negative. So that's not allowed. So what we've got to hope now is that when we do that out, this comes up to 1.10 times 10 to the minus 3 over 2. So 5.50 times 10 to the minus 4. That's x, and then, get out of room here. So pH is going to be equal to negative log of the hydronium ion. That's what X is. It's also the fluoride, but we don't care about that. The fluoride doesn't tell us anything extra, but we can learn the pH from H3O+. So what we got? Yep. And we get 3.26. So for these problems on the exam, most of them I'm going to ask for the pH. I could ask for pOH. I might do that for a base one. But pH is going to be, what is the pH of this, and of this acid solution, of this common ion problem, of the salt solution, of the buffer. It's just going to be pH over and over. So just be careful. Once in a while I'll ask for something else, but in this case, this one I think is plenty without doing anything different. All right, let's see here. So 6.8 times. And if using the approximation, you get pH is equal to 3.08. That's because it's power of 10. Let me see. Because we're talking about powers of 10 here. Oh, come on. God damn it. So do 3 point, let me just write it up here. So the difference is this. So it's going to be, actually it's going to be negative. just so I can see it here, because I'm messing up somehow. 8.32 times 10 to the minus 4, and then 3.26. This is 5.49. This is as an aside, which is a shame that I take so long to get here. So 8.3 divided by 5.5. So this is going to be 1.51 difference. Doesn't seem like much, but that is a 51% error. And in most cases, in analytical chemistry or physical chemistry, having a 51% error in your data would be monumental. So a big thing here is that this doesn't look that different. You say, oh, it's just slightly off, but that's actually, you're off by 50%. And it can get much worse than that. If this had been, instead of 1.47, it had been 0.007 or something like that, the lower it gets, the more off you will be. On the other hand, if you're taking a standardized exam and you had to do something like this and you were in a really big hurry and you needed to use the quadratic formula, you might go with the one that's closest. Use the approximation and take the answer that's closest to it. Sometimes they catch on to that. So this is the correct answer, and they'll have this wrong answer, and then they'll have 2 or 3 right in between. But yeah, if you're in a hurry, instead of doing out 2 minutes worth of calculation, just do the approximation and then guesstimate. But sometimes the test taker, the people who write the tests, are aware of that possibility. Okay, so, but there'll be one on the exam like this. You're going to have to do this out. The quadratic formula you'll have to do. And since you have to show your work, you don't want to just do that. You want to do this all out. But again, there won't be, for this, I think this is the only one I ask you to do, because there's so many to do in 17. Those 17 problems, there's just too many things going on, too many moving parts to have for the approximation not to work. So there'll just be one like this. So make sure you know how to do that. And the exam guide is written essentially in the order of everything that we see. So I would make sure, and you can see it's just, all I can do here on the exam is I change this. Right with this. I can change this. I can change this and this. That's it. So on the exam, whatever I gave you, I probably would write it out a little bit more lengthy there, but you're going to be doing this with whatever acid is here, and you probably just call it HA. You'll have a different number here, and a different number here, and then everything else is done the same way. So don't see it as you got all these different problems to do. This is one type with 3 different things I can change. Could certainly, and let me just say, when I took these exams, it wasn't like this. The professor would then say, "Oh, let's get a little tricky. Let's see if they're paying attention." And when I became a professor, I was at University of Michigan Flint, and there are these professors that would be walking down the hall and say, "I got something special for my students." I say, "What are you, a sadist? You're out of your mind?" And I say, because I think, well, as a student, I'd say, "Yeah, that's crazy," and then as a professor, I'd say, "Yeah, that is crazy. That's nuts." I'd say, "This is enough." I think for you to know, there's lots of ways of adding bells and whistles to make this. I mean, one thing I could do is just make this POH. And do like some of my professors that if you get it wrong, you just get all the points off and not even mention it. Oh, man. The thing that I probably mentioned this story before if you took me before, but it was the same professor. After one exam, he came back and he's just like, he had 100 students. And he says, and he's looking like somebody just stole his dog or something. He's just down. And I said, "Professor so-and-so, what's the matter?" He says, 10 of my students got A's. And he's looking at me like, "What happened?" He said, "I just wrote this up." So how could that happen? And I said, "Well, how many did you expect?" He said, "Well, out of 100, maybe 2 or 3. And he's just looking at me like, "What am I going to do?" I said, "Well, you're a full professor. You could do anything you want. No one's going to touch it." So he wasn't worried about his job. He was just like, he just couldn't understand it. He just wandered down the hallway. He's like, I wanted to say, I was on probation, but I was an adjunct there. I want to say, well, maybe you taught something this time. Maybe you accidentally went in there and taught something. Maybe that's what happened. Did you think of that? You actually went in there and gave them some information? Anyway. So, just things that I saw as a student's point of view and say, yeah, I was right. So I do like to, I'm not saying this is easier, that I did it perfectly here, but I certainly, this is the thing that you won't want to deal with. So if you have trouble with this, after class would be a good time to go through another one of these. If you're studying this and you want me to send you a problem like this, absolutely I'll do that. I don't give you the answer key because I don't know what the answer is. You send back the answer and I'll check it. So that's one that we need to do. Okay, so far, what have we done? We've done one where you are given the pH and you find Ka and the degree of ionization. And then we did the one that's where the approximation holds, one that it doesn't, and then we did the diprotic acid problem. And now we'll do the triprotic acid problem. So if everybody's good here. But if nothing, I think I'd really let you know what's on the exam. And as a student, I always appreciated that, having some clue what was going to be on there. But, whoops. All right, triprotic acid. So this one is like the diprotic, except we have one more step. We have 3 deprotonations we have to deal with. So we'll do a phosphoric acid that has 3 protons. We need 3 Kas, Ka1, Ka2, Ka3. Just because I did this pretty quickly. As you go from Ka1 to Ka3, these numbers get larger or smaller? Smaller. And that's always the case. Doesn't matter what the triprotic acid is. You can find 100 of them. They'll all do this. Because each time you remove an H+, it gets harder for another H+ to leave something that's negatively charged. So that's always going to be the case. That's a general rule that you should know. Okay, so what are... So this one, there's a ton of stuff here, but as we saw with the diprotic acid, most of what we need is learned in the first step. For this one, we're going to learn that we can know everything in the first step, but except for the last thing, and that has to be done in the last step. We got no choice. So the phosphate ion concentration is found in the last step. There's no way around that. And that's definitely on there. That's how it's going to be written on the exam. You're going to have to do the whole thing out. So, but if I didn't put that in there, you could actually technically find all the other 5 things without doing more than the first step. All right, I'm going to put these here so I can reach them as we need them here. And, all right, what are 4? Oh, I forgot to mention what we're doing here. So for a 5 molar, for 5 molar phosphoric acid, and then Ka1 is 6.9 times 10 to the minus 3. Ka2, so the Ks will be right in the problem. You won't have to look them up. But for the homework, you will have to go to a table. And I suggest using the table that they give you because they differ slightly from what's on OWL and what's in this book. And sometimes, not always. And then 4.8, 0 times 10 to the minus 13. I've never seen that make a difference in whether you get it right or wrong, but sometimes students wonder which one to use. Either of them should work. But here the problem for the exam, and all I can do, I can use this as another acid. I can use this. I can use this. I can make up some other ones. I've used this in the past. These ones I get actual numbers off of. This one I make them up because I can't really find it, but it should actually exist. So these are all triprotic acids. Who cares what they are? You just need to know the Ka1, Ka2, Ka3. And that's why you want to see this as it's a triprotic acid problem. What kind of triprotic acid doesn't matter. The only reason the species matters is what the Ks are. So I'll approach them the same way. But I will be writing out, just like I did for the diprotic acid, I'll write this out as the full form because it's just easier that way to keep track of these. But you are free to use H3A if you want, but when you do that, you're going to find that you're trying to figure out which ones are which here. So, all right, so we do this out. We got 5 molar. So we do the first step here, like so. And catch me if I make a mistake on these charges. I sometimes do. Let's see. So not that it won't make any difference to the math. I mean, the ratios are the same, but we want to make sure we know which ones are which. So that transferred over. That's right. So we have the ice table. 5 molar. I made this unusually large number here. Just make sure that we beat the approximation here. Approximation will hold for this one. Absolutely. No doubt about it. Doesn't have to, it just would be a nightmare otherwise. Doing 3 quadratic formulas each. So, there we are. Throwing it into the Ka expression, so it's going to look like this. So definitely here's a shortcut. I didn't write out the general form of it. You're free not to do, you don't have to do that. You can go right here. Just for form's sake, we can do the approximation, make sure that it does hold. But you are also free to just say approximation holds here. I trust that for something like this, you can tell the power orders of magnitude there without having to do the whole thing out. But you should mention that it does hold, and that's why you're going to get rid of that x. So do this out. Again, I'm going to do it fairly quickly here. On the exam, you don't have to write out every step. If you go right, don't square it. It's a bad move. Times 5. If you go right here, x is 0.186 molar. That's perfectly fine. So you'll have a full page to do this, but you want to be careful. Yeah.
Why did you use Ka1?
Oh, because it's the first deprotonation, so they go in order. This is for the first deprotonation, second, and third. Okay. Now, what we do need, though, is here. Not a huge change, but definitely something that registers. Whoops, minus 0.186. So this is going to be 4.81. Yeah. Okay, so don't put a square around that answer because that's the only one that's truly done. But we do know that those other two are going to round back. But for now, we just say this is the only one that we know. So without taking into account the rounding, or that there won't be any rounding we have to worry about, this is really the only one that we truly know for the first step, but we've already learned that these ones will not change very much at all. Yeah.
So on the exam, would you be able to put that as H0 plus and H2O4 minus or no?
Yeah.
Or would you want?
Yeah, no, that's fine. Yeah, as long as I can just see what you're doing with it. Yeah, there's no reason you have to write out this times this square root. You can certainly get here, and then x is equal to that. Well, what's x equal to that? You might put them up. You might just put them up here, like I did up here, because you have to find this. So, or you can just do this calculation down here. Anywhere where you show me that ultimately. If you tabulate them on the side, that's the most helpful. If I can just see those numbers, it is impossible that you guessed them. So if you get them all right, then I glance back real quick. If I just see these in a box around it, I'm going to then figure out who you were sitting next to. But everyone has a different, there's no way that you can possibly look on someone that's anywhere near you and get the correct answer. So I'll just say, wow, this person can do this all in their heads. Make sure you give me enough to work with, though. Yeah, if you just put down the answers, I say, well, they had to know it, and they had to know how to do it, but show me what you're doing. At least enough. Okay, so I can see where it goes. And then I won't be jealous that you could actually do all of this stuff in your head. Don't want to know. This guy in grad school, I came into grad school with a triple degree. It was chemistry, physics, and math. And he never used a calculator. And any time I did, he said, Mark, what are you doing? He said, I'm taking the square root. Fine, get out your calculator. And it's just so frustrating dealing with the guy. On the other hand, he was 6'4" and 300 pounds, so he played college football, so I never said anything to him. I said, yeah, you're right now. I'll try to get the square root of 5. No, Mark, not 5. Yeah, he was always disappointed. Okay. Anyway, all right, so this is now the second deprotonation. So this is the first step. If we had if we made this 3 and 3 here, we'd have phosphate here. So we need to break it into 3 steps because we need to, this step and this would not be shown in the overall reaction. So we're breaking the overall reaction down into 3 steps. Okay. What goes here? Yep. So we need to take, this is all happening, in matters of, probably nanoseconds at most, but we're taking it. So we think of this being produced and going over there. Anything else that goes over there? Yeah, the H, yeah. So you need, don't forget that this is all happening at once. So if these have been made, then it's over here. They're not, they're not happening on their own. Each individually, it's one step after another. So if these the dihydrogen phosphate ion is produced and hydronium ion is produced, and they appear in the next set, we have to put them in. The reason we don't put this in over there is there's no phosphoric acid. We're done with this. So the products here become, one becomes a reactant, one becomes a further product. So they get carried through. But then we do everything the same, minus X, plus X, plus X. Now this will be different than the diprotic acid one, a little bit, because we have one more step to do, but it's going to look very similar. All right, then we do this out, put it into the Ka2 expression for this problem. And this is dropped about 5 orders of magnitude and then 5 orders of magnitude. You look at any of these triprotic acids, they tend to do that. The Kas tend to drop by about 100,000 times each step. So this divided by 10 to the minus 8, you think that's greater than 100? Yeah, by tens of millions of times. So you can just say that the approximation holds. I'll trust that you can look at that and know that this divided by this and this number, say number, divided by this is greater than 100. So the approximation will hold, which means that we ignore this, and then these cancel because they're the same number. So X becomes Ka2. The only difference is that you have molars there. So the monohydrogen phosphate ion is determined from Ka2. Yeah.
You're able to cancel out even if it's plus X minus X?
Yeah, because it's just telling us, what this approximation is telling us is how small X is compared to this number. And it's teeny. Whether we add it or subtract, it's meaningless is what it's saying.
Okay, I see.
Yeah, so if we're adding on, and so we can see X is this. So adding this to this number or subtracting this from this number, it rounds back to 0.186.
Okay.
Yeah. So in reality, we do add to one and we do subtract from the other, but nothing that we can measure is what it comes down to. Okay, so we have this. So this is going to be the concentration of HPO4 2 minus. So this is going to be 6 point. So if the approximation held, then this X is meaningless. So to this, and this same thing here. And you can try adding that on. This number, like I did last time, I'm going to take 0.186 plus X is equal to 0.186 plus that number, which gives you 3, 4, 5, 6. That number. And it is, seems pretty reasonable to say that it's unchanged. And then this would have the same effect. It'd just be 1.185999999. So that's allowed. So we can see that this one is unchanged, so is this. We're going to have to take this on to the next deprotonation, but it's going to be even worse because the Ka3 is smaller. But let's look over here. So the last hydrogen there, that's still, so this was the conjugate base of what came before it, and that was the conjugate base of the phosphoric acid, but this is also an acid in its own right, not very strong, doesn't do very much, but it definitely does deprotonate to a degree. So we got to figure out how much. So what's this number here? What is that? Well, yeah, 6. Yeah, so teeny tiny. What about this guy?
0.86.
Yeah, 0.18. So a lot of times students they're now in the groove here. So they'll take that number, put it here, but you can see now we can't lose. This was already in place. We had 0.186 from the first step. We added on such a tiny amount that it essentially rounded back to what it was. So this 0.186 gets carried through twice, and this is 0. Okay, so since there's H2PO4 minus is not in here, then this one's done. And we can add this in. This is 0.186. All right. Yeah. We know this is still 0.186, but I just want to show that you go all the way through and you can add on as much as you want along the way, but each time it's smaller and smaller, so it is unaffected. This one we need the third step, and then this one is from the, we still have to check on this one. We know that it's going to round away, but let's just prove that. So this is minus x, plus x, plus x, one last time. So diprotic acid ends there, but this one is triprotic acid, so we keep going. And this is a good one because now we have something where that Ka2 is not playing a part, and these numbers are not the same, so they're not going to cancel, but we still do the same kind of stuff. Ka3. Hopefully on the exam you're not writing on the wall like I am. You're writing on 3 big bed sheets. Can't see what you started with. But when you're doing this, try to keep it organized and make sure you're using the correct Ka as you go. Okay, so now we do the same thing. This divided by this number, definitely greater than 100. What about this tiny number divided by this? Is that going to be greater than 100? This is 10 to the minus 8 divided by 10 to the minus 13, so it's like 100,000, so absolutely. So even though and you can check it to see. So if you did this, just as this one I know, but this one I'm not sure. These are both tiny numbers, so let's see. But it will hold. So approximation does hold. And we certainly know that it does for the top one. So this is gone. This is gone. So it's a little bit more complex. These don't cancel this time, but it's still, the math is fairly simple. Just got to be careful. Times 6.2 times 10 to the minus 8. This times this, and then divided by 0.186. So x, which is, so x is 1.60 times 10 to the minus 19. So phosphate is 10 to the minus 19. Now, this is now theoretical. There's no way of measuring this. We just go by the theoretical. There's ways of backing it out through electrochemistry, electrochemical reactions we could do. Look at that here. But you can't measure that. So as we are doing it in our lab, we have to trust that that's the case. Okay, and then we also see that this is going to be, and this is going to be unaffected. This is the easy one to do. So 0.186 plus 1.06 times 10 to the minus 19 is equal to 0.186 say that's fair to round it back to 0.186. You can't even fit that onto your graphing calculator. You can't. So yes, this is. We have to say that since we can't actually measure this normally, and it's way below this, 17 orders of magnitude that we have to round to, that would be good. So we've proven that H3O plus doesn't change through this reaction. We have this guy here. This one is unaffected. So that's our last term as well. So we have everything now. So, what is it, 6.2 times 10 to the minus 8. What was it, 1.6? Yeah. 1.60 times 10 to the minus 19. H3O plus we learned from the first step, so this is 0.186. And then pH we can find. So the pH is 0.730. I think that's right. It should be low. So that's everybody. But again, this is found in the first step. This one's found in the first step. This one's found in the first step. This is third step, and then this one we can argue that it's the 0th step because you can find this one out just because this is just Ka2. So if on the exam, I'm going to make you do it all out, but if I want to, say, oh, okay, they got other things to do, I could just ask, what's the concentration of this? Just to check, make sure you know what you're doing, and you could just write off Ka2, add molar to it, and you're done. I've got to see this from a distance. I always like that. On this one, I'm in American House. Did I get that far? Nice. I think everything's there. So this is a good one to try out because it's worth a lot of points. It's one that really is just 3 of the problems that we've done. And notice we've done the same problem over and over. Minus x plus x plus x. Minus x plus x plus x. Change the k's. Change a few little things here. We've got these. We have to take the information from here to go to there. But same problem. So we've done, what is that? 2, 3, 4, 7 times we've done the same calculation. And we'll do a lot more. So you want to get into thinking in those terms, that minus x plus x. You're just using whatever the k is. We're going to do a common ion one, but we've already done it. Here is where we have a number on the right side. And all that did was make it a little simpler because we could forget about the x here. Same thing here. We have this on this side now, but that only made it easier because the approximation covered it. Now it's not even x squared. We don't even have to take the square root now. So having something on the right looks like it's going to be busier and tougher, but it always comes out to be easier because of the approximation. Yeah. Okay. Good stuff. And if you can do this, I'd argue you're probably, quite literally, 1 in a million. How many people on this planet know how to do this? Not very many. Not a lot of people are going to be bragging about it, but I mean, you have to take the stats. And the stats are that you're probably less than 1 in a million. Or 1 in a million or maybe less that can do this. Yeah, put that in your resume. Boom. Just take a picture of it, staple it on there. And if they say anything, say, well, can you do this? No. See? Okay, so, and the other thing is that this is the true chemistry. This is something that actually you need to know if you're dealing with polyprotic acids. And though you probably wouldn't do this calculation, a computer would be doing it for you for whatever analytical device you're working with. Okay, so any questions on this? Because that's it. I did a diprotic acid one, mainly so that you know how to do it on the homework, but this is the one that's going to be on the exam. Okay. Okay. What else do we have here? Triprotic acid, we did that stuff. Let's see what's on the exam guide. Yep, did that. Okay, now the bases, the weak bases do the same. The math is the same when we get down to it, so it's pretty close to what we've had to do. So, but let me just write out, so for the acid ionization, it looks like this. Here's the reaction. And then here's the acid ionization constant expression. Like so. If we have a weak base, you write it like this, B plus water. This time water acts as the acid. It gives up an H plus. Here's your weak base. Here's its conjugate acid. Here's the acid. The conjugate base of water is hydroxide. And that's what determines the basicity of the reaction. So this is the acid ionization or dissociation. Acid ionization reaction. This is the acid ionization constant, so you should know the names of these things. And then this is the acid ionization constant expression. Okay, and then this is the base ionization reaction. There. So we have K. I'm going to write it as it appears, so it looks very similar to what's above there. So we have hydronium, hydroxide, conjugate base, conjugate acid, weak base. So what should we call this guy? Kb. So Ka, they're both Kcs. They're both equilibrium constants based off of concentration, but since they're special, we're dealing with an acid and a base, we give them special distinguishing marks of A for subscript and B subscript here. So this is going to be the acid or the base ionization constant. And the base ionization constant expression. So I think write the chemical equation showing the general base ionization equilibrium in aqueous solution. Write the corresponding equilibrium constant expression. So just this and this. That's definitely quite possibly verbatim on the exam. I don't know what else I could do there. I want to see that, so that's a very likely thing. Could certainly make it multiple choice. That is possible. Where among all the possibilities, this is one of the 4 for the multiple choice. But usually I just have you write them out. But if you can write them out, you can answer any multiple choice question or any other format. Okay, so I don't spend a lot of time on this because you can see that it's going to work about the same way. But let's do out a base ionization reaction problem, and then we'll take a break. So let's see. What is the pH of a 0.15 molar, I should say, of 0.15 molar ammonia? And then say Kb is going to be 1.80 times 10 to the minus 5. So it's a base. Whoops. And how do you know that that's a base? If you didn't see ammonia, or you didn't know ammonia was a base, how do you know that you're dealing with a base? Was that? Kb. Yeah, you see Kb. Absolutely. That tells you what it is. So, the information will be in there. So ammonia plus water and I almost always use ammonia because the weak bases tend to get pretty gigantic pretty fast. I know the homework sometimes they'll give you these pyridine, it'll be some monster molecule, but it's just whatever that monster molecule is with an H plus attached. But so we have 0.15 minus x plus x plus x. Oops. X and x. The Kb expression this, and that's equal to 1.8. So right here, if you had come in and you didn't know what we were doing, and I just erased this, and I just gave you this, and so, oh, another Ka problem. The math is exactly the same. It's just what you're finding is different. So let's do this out. We can use the approximation because the approximation is based on this equation, this mathematical equation, not where we got it from. If we just made this up without anything else, then we know that if this number divided by this number is greater than 100, removing this will give us less than a 5% error. It doesn't matter if it's hooked up to a chemical reaction or not. Okay, so we can see that this divided by this is going to be greater than 100. So we can say the approximation definitely holds. So we get x squared, 0.15, 1.8 times 10 to the minus 5. So 1.8 times 10 to the minus 5 times 0.15 square root. So x is going to be 1.64 times 10 to the minus 3 molar. We take the negative log, and we see the pH of this basic solution is very acidic. This is the biggest mistake that's made. What did we find for x? What is x here?
Concentration of hydroxide.
Yeah. Up to now, all we had to do was find x, take the negative log of it. So this is wrong. This is... So what we can say, if we take the negative log of this concentration, I should have erased it, so 1.64. So what is that equal to? It's not pH. pH. And that's certainly what I could be asking on the, so check and see what it is, but I wanted pH, I usually do. So what you found is POH. That's not what, so you wanted pH, so that's going to be 14 minus POH. So, and that makes more sense, pH. And the reason I have you change it to pH, first is that make sure that you can do that. Second, that's a lot easier for me to tell if it's right off the bat when I see that, because I like to work in pH. But it's rare, most people don't work in scales of POH. But that's what you did find. That's what you're going to find for this problem, so you have one more step. But if I had asked for POH, then that 2.79 is what you want. So on that kind of problem, I can't promise anything. It could be either way. Sometimes I just say POH because I'm trying to make it easier on you, and then people will subtract from 14 and make that mistake, so be careful, yeah.
What you had on the bottom was just the same thing, except you said it was 2.79 on the bottom.
Yeah, and I labeled it as pH rather than
but it's
POH.
POH,
Yeah.
okay.
Yeah. But it's just that students do make that mistake. They take the negative log of it, and boom, done, that's pH, because that's always been the case up to here. Here we have, and that's what we're going to find as we do more and more of these problems. We usually have like one extra little step to do, but if you miss it, it's a big deal. Okay, let's take a 10-minute break here, and we'll do these salt solutions.
Stapler?
No, I don't. But if you want to write your name on each of the sheets, that's
Okay.
all you need.
Do you have a stapler?
Nope, just write your name on each
Stapler
of
right
the
here.
sheets and it should be fine.
He had one.
Go on. Good.
Thank you so
Yeah, make sure you return that.
Okay, I can go.
Yep, yeah. What's up?
Quick question. So when I did the lab, I calculated it out and I got 268%. And I have no clue where I went. This is for a lab grade.
When you did the second calculation, did you use 48,441?
No, I did not. I used that.
You used it as 48?
Is a rate constant? And
Yeah,
just
it's in joules.
Oh.
You like to write it like this at the end because it's nicer. But when you do the calculation, so redo it with the.
All right.
Sorry about that.
Do you mind if I bigger?
What's
The
that?
test, do you mind if I bigger?
Yeah, just then we'll probably get to. Definitely gonna do that. We'll get at least to. We'll get through here. I don't think we'll do the buffers. We should get to common ion effect. So use the videos to catch up. You gonna take off now, or are you?
Yeah, I'm trying to go to the learning center to
Yeah.
take the test.
Yep. And then if you're doing that, then it'll be done by the time before I leave today. So I'll pick it up. I should have it graded by tomorrow. Okay.
See ya.
Yeah, exactly. Come out of like 9 hours, you have to go back and another. How long is it? A Friday?
Okay, so I just have a question. So you know how you have to check for approximations for both of these when you have like an X on the bottom and one on the top? So if you find that this holds, does that automatically do the
It does,
as
yeah,
well?
yeah, because if you're taking this divided by this, and it was greater than 100, then a number that's greater than that has to hold. So,
Okay, so is it the
Right.
same with the top as well? So if this was,
Yeah.
if this held, then this would hold too?
no, because it goes the other way. This divided by that number gives greater than 100, but this is smaller,
So you always
so
check the
it's going to
smallest
drop. Yeah,
and
so
then
go
the
with the
smallest
smallest.
one
Yeah, if you do the smallest one, then and it holds, then the one that's larger has to as well.
Okay, that makes sense. Thank you.
Yep. Yeah.
This right here, he didn't bring it to 87. When I do this. But I think that this number is supposed to be something different.
And you use that. Let's see. Those seem okay. That's how you-
That'd be really weird if it was me first. That'd be
We'll
really
just leave constant of this constant, got it. And this is 312.
How does it look old or it's still like 90% out by the Yeah, it's normally an engineer reports and they literally just found that on the side of the road and like a dog and then teach it. It's not almost funny to teach those. It's his first time teaching others. I assume so. So it doesn't have to be
And where is, and then your data showed it as this. Wait, where'd you get this number from?
I'm supposed to use this number?
Yeah.
I think I used this one.
Oh, yeah, yeah, there you go. Yeah, that's better, because everything else was perfect. So,
Yeah, I'm like, something's off here.
Yeah, that should get you under, it looks like under 8% then.
Okay.
Can I see my exam? Thank you.
Did you look at it before?
Can you go over this with me? Finding grade 3, and then the
Okay, so you did this out. These are your numbers from,
I
okay, there's something amiss here, because it should be plus 273, so that might be throwing you off. So yeah, here's
Oh, yeah,
your
right.
temperature. Yeah, so this should be.
That should be,
But yeah,
I'm looking right here, 278.
Yeah, so this should be 21. So this would be 294.
It was like weird.
This should be 296. This should be 294. And then 278 here.
And this was supposed to be.
This is 294 up here, and then this would be 298 below. And then 278 and 278. That's because that'll make a big difference. And then 312 and 311. Here, so you're finding something that was wrong or didn't seem right as far as your error was off.
Wait, do I just type it in the thing? Yeah.
That actually wasn't my question at all, but now it shows everything else, so now I have to redo this, but I was having a hard time finding the degree.
Okay, so you found this, that looks like you double checked that'll be changed, so that's right. And then you just leave this one alone, and this value, these are matched up. So it would be this and then be 220 or whatever it actually is. And then you're going to put in the hot temperature here and solve for that. So your hot temperature was 3, yeah, this should be 311 here. So you can use either one. You can
Numbers are
average
not working for me.
I'd say that make this 312 here.
Okay.
And then this should be yeah, 2 different temperatures, but say so the 294 and 294 here, and then put in 312, and then solve for that.
Sorry. Can I give this to you after class?
Yeah.
I just want to make sure of the calculation.
Yeah, that looks like you're in the ballpark. It'd be tens of thousands of joules. So, oh, yeah, you changed it. Good.
And then I took the ln of this number,
Right.
finger 1, and then I multiplied with 8.31, and then equals to, I get 2.18, 1377, and then
Yeah. Yeah. That's good.
I think I'll grab one, right?
Oh, that mine? Yeah, that's what we're doing today.
But this is the number.
Yes.
Do you have a staple?
No, just put your name on the sheets, or on each of the sheets, and then you can turn it in.
Okay.
Gotta do that. Thank you.
So I did the calculations. It's measured, so that's our measured value.
Right.
Subtracted by our calculated, divided by calculated. Still got somewhere around 2.34. That's before the multiplying by 100 though. So, because
these are all the same order of magnitude.
unless I'm plugging it in wrong into the.
I get 0.34, so 34%.
So somewhere in the calculator.
Yeah, double check that and see. And then it should be absolute values.
Absolute value, yes. Okay. Thank you.
Because then I started thinking, and I'm like, no, like something I'm like,
Yeah, it's
These are my chairs, so I don't know.
Oh, okay. Grab some water.
because I mean, She has for us, and that's my. I mean, my mom gave me too. If you want, you guys can go and I'll just chill with you. Like, I really don't want
Next semester here.
Why were you like 2 days late today?
Because I was
Watching this movie.
yeah, I was watching my niece first, and then I was confused.
Yeah, I don't know. I went over for
I figured it was just one little but it was just something I got hurt.
No, they give you yeah, they weren't there. No, that's what they like pay for most of the you still get everything that you have in water right now. You usually just have to pay the same amount. Because they give you some. I mean, it's cool.
Okay, here we go. What are you doing?
Yep, hit 70,000 steps since the beginning of the semester. Tally up now. This is since 2 Sundays ago. I just forgot to reset it. But still, 70,000. All right. Okay. All right. So we'll do salts and start into buffers, and then I'm going to go through the calculation for lab 4. I'll do about that, but let's do the salts. So there's a qualitative part and then the quantitative part. I should say. Okay, so salts, any inorganic compound that we can put into water, it's either going to have an acidic pH, neutral, or basic. So before we, so you should be able to look at any ionic compound and say that if it goes into solution, what's it going to do to the solution? Okay, so finding the acid-base parents of salts. So remember from 1170, chapter 4, an acid plus a base will give a salt and usually water. But every salt is born of an acid and base reaction. It's the product of it. So any salt that we have, we can backtrack. We could make it, theoretically, we could make it from an acid and base. And a lot of salts are. A lot of compounds are made that way. It's just the easiest way to do it. Okay, so if we have a salt, let's take the simplest one, the one that we just call salt. But salt is any inorganic compound made in a neutralization reaction. What you do is you just separate the cation and anion. And then the cation, we add OH minus to. And that makes it NaOH. And then to the anion, we add H plus. And that gives us HCl. Those are the parents. So if you're unsure if that's true, then take HCl plus NaOH. This is a double replacement reaction, so switch the partners. Going way back to chapter 4. And yep, we make salt from hydrochloric acid and sodium hydroxide. And this one, that reaction always, when I first got here about 18 years ago, there was a chemist that had just retired, and what he'd had the students do is they do their titrations. And once they had made their salt, they did this titration. Once they had this, he would have his students drink the solution. Because once it was neutral, it's just sodium chloride. It's just salt water. And I was like, what in the hell? And I go, what? And now he's right. If everything was absolutely perfect, then you would be drinking pure, only sodium chloride. And I thought the person who told me was just joking around, but I found out it's actually part of the lab technique. Things have changed. And they had changed long before that professor did that, but that professor had been teaching since the 60s. So yeah, things are a little, safety rules were, I guess, a little more lax. It's like if you just had a little bit of extra of this or this, then you have much more than a salty solution you're drinking. But anyway, so that's horrible. All right, but the fact is he's relying on these acid-base parents to create that salt. Okay, so we can do this with any salt. Let's do one that's a little more complex. Don't worry about the subscript. What should be the parent base here? Just got to make sure you know the charges on here. That's LiO, so that's lithium hydroxide. And then what should this one be? Yeah, it's going to be, and you add in H pluses until it's neutral. So this is H2SO4. So that would be, the parents there would be lithium hydroxide and sulfuric acid. Let's see, so if we have, do this one, okay, this one's a little different. If you add in OH minus to it, it becomes NH4 NH4OH, but this is really just ammonia. Ammonia, when it goes into water, forms a small amount of ammonium hydroxide, but you're free to call you can certainly name the parent ammonium hydroxide, but the real parent would be NH3. And then the acid would be this. So, again, double check. Here's our salt, and then 2 waters. Here we have ammonia plus HBr. And in this case, it only produces the salt. There's no water because there's no OH minus attached to it. So the parent here is ammonia for that base. Okay, so you should be able to find the parents. Let's do something. So if we have, it can be anything really. Any salt at all. Here's copper 2 acetate. So where did it come from? Well, it came from copper 2 hydroxide. That is a base. It's a weak base. And then we have acetic acid. So whatever the salt is, we should be able to determine what the parents are. And then once we know the parents, whether they're strong or weak, that will tell us the pH of the solution. So you should be able to find the parents. And then once we know the parents, we can determine the pH. So let's do one out. Let's go back to NaCl again. So that's going to be, the parents are going to be sodium hydroxide and HCl. This is a strong base. This is a strong acid. So think of it in terms of the strength of these things. The strong and strong, they cancel each other out. So the pH is 7. This is neutral. So strong acid and strong base parents, they essentially neutralize each other, nullify each other. And then if we have this, break it up into its cation and anion. This becomes KOH, acetic acid. Is this a strong base? You don't know if this is a strong base? This as the problem. Yeah, so strong. Make sure you know the strong acids and strong bases. That is a problem on the exam. Is this a strong acid? No, this is a weak acid. Okay, so now just thinking in terms of the strength of it, we have a strong base versus a weak acid. So the strong base wins out. So the pH is greater than 7. This is basic. So it's basic because the strong base wins. And then if we have something, yeah. So we have this. This is going to be ammonia, and this is going to be HI. This is a weak base. Strong acid. Did you know? Yes, strong acid. So the strength of the acid wins out. So this is going to be acidic, which means that the pH is going to be less than 7. So what we've done is strong base, strong acid, strong base, weak acid, weak base, strong acid. So the last one would be something like this. These arrows really weird. Arrow. Weak base and weak acid. Okay, now this one. We don't know without further information. So these ones we can tell. The reason is, well, I'll show you in a second, but this is called, this is hydrolysis reactions. Here, there's no hydrolysis reaction. Hydrolysis means the breaking of water. So breaking it into H plus or OH minus. Here, nothing happens. Here, the strong base produces OH minus in solution. So it becomes basic. This one, the strong acid causes the H plus to be produced, so it's acidic. Here, both of these happen at the same time. And they can't, so we need to know something more about these. So what we've been saying here is qualitative. And it's just a way of remembering it, but what's really happening are these, what are called hydrolysis reactions. But this will work. You just look at the strength of these things. Whichever one has the strong acid or strong base, that's one that wins out. If they're both strong, they cancel. But weak base and weak acid, a little bit more to it. So let's look at the hydrolysis reactions. So just kind of working our way up. So the first thing is just qualitative, and it works for 3 out of 4 of the combinations of acids and bases. But the fourth one, we need to know a little bit more. So if we look at this, sodium chloride goes into water, and it breaks up into sodium ion and chloride ion. Now, hydrolysis says those ions will go on and they will react with water to do something else. So let's see what can happen. So Na plus water. Well, water contains only 2 things that can be produced in solution, H plus and OH minus. Well, the sodium ion, will that react with the H plus? No, I can't get near it. So the only thing it could do is essentially steal away an OH minus from water. So if it did that, it would produce NaOH plus H plus. Now there's a problem with that. Actually, there's 2 problems with that. What's a problem here if we produce sodium hydroxide in solution? We're saying it comes together as that compound. If you could actually produce sodium hydroxide in solution, what would it immediately do? Would it stay together as one formula unit or molecule? Or would yeah, it's a strong base. So it immediately shift back this way. So and then the H plus is another thing. That's the strongest acid that there is. So this is no reaction. Sodium ion goes into water. The only thing it can produce is sodium hydroxide, which would instantly break apart. So it's not possible. How about this chloride ion? Well, all it could do is produce HClO and then OH minus. So again, produce one of the strongest acids available and the strongest base, which would neutralize each other. And this would ionize and shift back, so no reaction. So no H3O plus and no OH minus are produced. So that's why it's neutral. So there's no, so you can say is no hydrolysis. That is no breaking up of the water. No hydrolysis, neutral solution. So when you have a strong acid and a strong base that produce a salt, and so there's 36 possibilities, and you put any of those 36 salts into solution, they just remain pH 7. Okay, if we do next one here, so this salt goes into water. It produces K plus. Get a little lazy here. We need liquid. Okay. And there's no return arrow here. This is 100% dissociation. This is a soluble salt, so it breaks up into its ions 100%. And then we look at each ion. So the potassium reacts with water, and the only thing that it can produce is KOH, a strong base, so that tells you no reaction. So far, it seems like nothing's going to happen. Then we look at the acetic acid, and this reaction is what causes the common ion effect and buffer solutions to exist. So it becomes really important. This hydrolysis is very important. And this actually has a return arrow. A weak acid likes to be in this form. So if you put the conjugate base of a weak acid into solution as a salt, it's going to scrounge around and find H plus wherever it can, only on the water. It takes up that H plus, becomes its former self, that's what it wants to be, and in the process produces a small amount of OH minus. This didn't do anything, this produced OH minus, so this becomes basic. So this strong base did nothing, or the part that could have become a strong base does nothing. This part becomes a weak acid, and in the process, it wants to be this so badly, it's willing to strip away an H plus from the water and leave an OH minus, so it becomes basic. So that's really what's happening. But thinking of it as weak and strong and weak really works out pretty well. Looking at this salt. This breaks up into ammonium ion and iodide. We'll do iodide first because nothing's going to happen here. All it can do is produce HI, which it's not going to do because that's a strong acid that would dissociate immediately, so no reaction there. And then the ammonium this is trying to get back to ammonia. Ammonia is the weak base. So this is the conjugate acid of a weak base. It wants to be in its original form, so it's going to transfer an H plus. So this becomes ammonia. It's happy to be there. And in the process, it produces some H3O plus. That's the acidic part, so this becomes acidic. Okay, so the last one is ammonium cyanide. That breaks up into ammonium ion. We already know what that does. And then the cyanide. Okay, so now you have two ions that are going to hydrolyze. Before we had either none, one at a time. Now we have both, so they're competing. The ammonium becomes ammonia in water. It produces ammonia and H3O plus. And then the cyanide produces HCN and OH minus. So this produces H3O plus to make it acidic. This produces OH minus to make it basic. So which one wins out? Well, it's going to depend on their Ka and Kb values. So if we look at these, we find that Kb for this is 1.8 times 10 to the minus 5. And then this Ka is 4.9 times 10 to the minus 10. So just looking at these, Kb is greater than Ka. So Kb wins, so this is going to be basic. So if you want to determine, so if it's a weak and weak, you look at the Ka and Kb, and whichever one is larger, if the Kb is larger, then it's going to be basic. So that's what you'd have to do. So if I give you this one, if I ask you which is it acidic, basic, or neutral, you would have to, you either have to say, can't tell you, or I give you these K values, you compare the K values. So let me give you a, let's get a Kb. We'll do another one, because these other ones just is just qualitative. Is this okay as far as? So you just have to know what the parents are. So these three, no problem. I could ask you what happens in the solution, so you want to make sure that you can say which one of these ions breaks up. And we're going to need it for the base, for the common ion problems and the buffer problems, so you're going to need to know these. But these are the only ones where you need to know the Ka values and Kb values. So let's do one here. Let's do it over here. Do something horrendous here. Okay. This is a mix of aniline and nitrous acid. Aniline is the thing on the left there. Nitrous acid gives that NO2. So it's horrible looking. So if I said, what's the solution there? Well, you know that since here represents the base, so this is actually the base, C6H5NH2. So this is the base. Actually, why don't you put that? And then this is the acid part. Okay, so looking at that, it's like, I don't know. You don't have to know. What I would then have to tell you is that Kb for C6H5 is equal to 4.20 times 10 to the minus 10. And then Ka for HNO2 is 4.5 times 10 to the minus 4. Okay. So a whole bunch of stuff on there. Is it acidic, basic, or neutral? Acidic. It doesn't matter. I mean, I could just spill my coffee on this. You get the exam, and this is all covered with a coffee ring. And but you know that I'm asking, is it acidic, basic, or neutral? You just look at the Ka. See, Ka is greater than Kb, then it's acidic. Not that I put those monsters on there, but they do something like that can show up on the homework. It doesn't matter when aniline here and nitrous acid come together, they form this monstrosity. So what? We're just looking at the Ka and Kb. And second thing is, how do you know that this is a salt of a weak acid and a weak base? How do you know that? And maybe this is something we should talk about too. The Ka and Kb are always for weak. We don't have Kas for strong acids. We don't have Kbs for strong bases. So these must be weak. Since they're weak, then you just have to study their Ka and Kb. Whichever one is larger, that tells you, in this case, Ka is larger, so it's acidic. Okay. Now, and that's something I should point out because it's never listed anywhere. No one ever says this. So it's a good thing to know. What is Ka for a strong acid? All of the Kas we come across are always weak acids. The table has only weak acids. They don't show Kas for strong acids. So we picture one of the strong acids we know best. Put it as equilibrium here. Put in here. No, it's a good one to know. It's an aside, really, but it certainly could be on the exam. Okay. At equilibrium, how much of this is left for a strong acid? 0. So that's 0. So the Ka is essentially infinite. Well, it's not quite. So Ka turns out that actually there is a small amount. Ka for HCl is about 10 to the 6th. It's a million. HCl, sorry. Ka for Hi is 10 to the, I think it's 10 to the 8th. Might be 10 to the 9th. But it doesn't really matter. What it says is that so in the chapter 15, we just said it dissociated 100%. If we take this into account, then we would say it dissociated 99.99%. And we just round. So Kas for strong acids are not infinite, but for all intents and purposes they are. That's why we don't include them. That's why you'll never see them. Because they're so gigantic. If you wanted to do it, you could. But what you're going to end up with is these, so if this is 1 molar to start, and this is 0 and 0, then you're going to get rid of 1 molar. This would be 1 molar. Actually, you do X plus X plus X. And what you find is that X is going to be 0.999. It might even be more. For this one, it definitely would be. It'd be something like that. And so if you wanted to do out the math, you'd say, okay, it rounds to 1. And this is going to be 0.000001. So it's good to know that Ka is not infinite for strong acids, but it's so gigantic that we don't tabulate them. But and when I was doing this, I wanted to find Ka for HCl. I looked online for quite a while before I could find it tabulated somewhere. I knew it wasn't infinite, but I couldn't find it anywhere. And so all these strong acids and so perchloric acid is going to be even larger than this. So not that it's on the exam, but if you ever come across, so why don't they put Ka for HCl on there? Because we pretend like it's infinite, but it is so gigantic of a number that it's pointless to use it. Though on the exam, if you want to take the time to do that, you can. You're just going to eat up a lot of time putting in these gigantic numbers, and they're going to round back to what we say they are. But weak acids and weak bases do definitely have Kas and Kbs that we have to keep track of. Okay, so this was just an aside. Okay, let's do out a little bit, get closer to the buffers. The buffers are the big problems of the semester. The buffer problem is got to be the toughest one, but we'll take it a step at a time. And the videos do help, I know that. When I first started here, we had the exam, and people would leave the buffer problem blank, and there'd be page after page blank. And somebody actually left the exam crying. I said, "Oh, that's not good. That doesn't." And I looked at it and I said, "Holy cow!" And what did it? I made up the videos specifically for that. It's very rare for anyone to leave it blank. Now everyone at least gets started on it. So use the videos. That's one of the videos that gets the most views. It's not the most, though. The one from 1060 with a ring formation for monosaccharides is in the 20,000s. I actually got an email from YouTube congratulating me. I thought they were messing with me. I said, "Oh, come on," because most of my videos are like 35 views. I say, "Is somebody messing with me from YouTube?" And look, it's like 20,000. That one I had to redo about 3 times to get it right so people could understand it. Yeah.
Is 1060 Orgo 1 here?
That is Intro to Organic and Biochemistry. So that is the second part of 1050, but it's an intro to organic. The organic is that's a 200 level, so that's 2260, 2270, and 2280. But some people, if you can take it, it helps out for preparing for the organic. The last chapter that we do is organic chemistry, and I do the naming and structures, and that students tell me that it helps them a lot. But yeah, was there a? Oh, okay. Sorry. There's a bottle was dented in, and I just can't take that. It's driving me nuts. I'm telling the students that in the morning that I'm borderline hypochondriac. So I said, "What's that?" I said, "Well, that's where you fear illness, but to a ridiculous way. Like if I drop this marker out in the hallway, I'm not picking it up. I'm leaving it. I'm not taking the chance. I drop it here, it's okay. Yeah, that shows it's an illness. But I do my therapy as I can. So if you see me dropping my marker, just watch. I'll pick it up. It'll take me a bit. I said, no, therapy. Come on. You got to be able to function in society. But yeah, it's gotta keep track of these things. But yeah. And the other thing is slightly obsessive compulsive, like this dent in my bottle. That was time as I could see it from the other room. So I don't know what I said over there because I could just see that it was dented. Anyway, I digress. All right, the last thing that we're going to do here is and then after that, you're free to go, but I'm going to do the calculations for Lab 4 after that. So let's do these out. Common ion effect. This takes us closer to buffers. There's one that is really a buffer, and then the other is a little different, has a trick to it, so I want to make sure we cover that. So common ion effect. So, I'll make it easy. So let's say that. So what is the pH of a solution that is 0.1 molar HCl and 0.1 molar HF? Now the HCl is a strong acid, so it's going to dissociate 100%. We're going to pretend like it does, but it is like 99.99% of this. So this is immediately going to go into water. All of this is it's gone. We get 0.1 molar H3O+, 0.1 molar chloride. And we don't care about the chloride. The chloride doesn't affect anything. So we have the HF expression. Okay, so we see that HCl creates H3O+, HF does too. That's the common ion. So they share that common ion. So the common ion will appear on the right side, and we have to take into account both concentrations here. What goes here? Normally it's 0, but this time HF has HCl as part of the solution. Yeah, so we have to include this. So let me finish the expression here. So it's minus x plus x plus x. So the hydrofluoric acid is going to add x to this. That's where the H3O+ comes here. But then the other HCl produces this too. So they both produce the same ion. That's the common ion. Okay. Now, let's do this out. Now, there's a trick to this. I'm going to do it. I'm going to do everything out, but then I'm going to interpret it wrong. So let's take a look here. And KF, sorry, so KA for, and in this case I'd have to let you know, KA for HF, just so that there's no confusion about the HCl. Let's find that. HF is 6.8. And just so we don't have to keep going back to it, the approximation is going to hold here. But, so 6.80 times 10 to the minus 4. This divided by that is going to be, the approximation is going to hold. This divided by this approximation holds, so x, and in this case they just happen to be the same. Didn't mean to do that, but that's okay. So x is going to be 6.8. Okay. So I take the negative log of that. This is wrong. So the pH I'm saying is 3.17, but that's wrong because this is a common ion. If it was just HF, yeah, we'd trust that. But what did I forget here? Before we take the negative log, what we're trying to do is find the concentration of H3O plus. That's normally X, but what is it here?
We have to add.
Yeah, and you can see that 0.1 came from the acid, and it's way more than this. So if we do this out, we see it's 0.1 plus 6.80 times 10 to the minus 4. So this is 0.01. So it doesn't change very much, 0.10068. Take the log. And the pH, so this is wrong. pH is 0.997, which you can really rounds back to 1. What's the pH of something that's 0.1 molar acetic, strong acid? And this is just the power of 10. So this is 10 to the minus 1. So the pH is going to be 1. So the pH So instead of doing all of this out, and this is perfectly legal on the exam, if I give you this and I ask for the pH, just take this number, take the negative log of it, and that's your pH. You don't actually have to do this, because the only thing that changed here is this minor thing that's going to round back to the original, to the number. So, does that make sense? Yeah, so this H3O plus is what gives us the pH. But the vast, vast majority of it comes from the strong acid. That's the 0.1. This weak acid provided 6.8 times 10 to the minus 4, almost nothing. So when we take the negative log of this, it's essentially like taking the negative log of this. We came up with this value, which would round to here. So the pH is determined by the concentration of the strong acid. The only reason actually that this part had any part to play is that I picked one that had a Ka that's pretty large. If this is 10 to the minus 5 or 6, it would be so small it wouldn't even register. So on this problem, on the exam, if I ask you for the pH, you just look at the strong acid, take the negative log of its concentration, and you're done. Now, on this one, if I ask for the concentration of the F minus, then you have to do X. But odds are for that problem, I'm looking to reduce the time you're going to be needing to do the calculation, because you had other things to do. This is just a nice common ion one, and this is meant to be a fairly quick one. But this one is not as useful as a common ion effect, because the other common ion effect one is a buffer, and that's what we want to do. So this one is a standout. The common ion here is the H3O plus. The one that we're looking for is usually the common ion is the conjugate base. So let's see what we have here. What is the pH of a solution that is 0.4 molar So most of the problems that we've done so far, it's just been one species, either one one acid, one base, or but in this case it's two things. And so when you have this, I said it's the Ka for this, so draw the Ka expression, because that's what we're going to be calculating with. So we do this, and we put in the values, 0.4. Now that Na, this salt, sodium acetate, is going to break up into sodium ion and acetate ion. And so if this is 0.6, these are both going to add to 0.6. So the concentration of the acetate ion is going to be the same as the salt. So you can see that this comes down here, and then this one comes here. That's the common ion. Acetic acid is going to produce the acetate ion. That's what the Ka expression shows. But this acetate, the sodium is a spectator ion. This acetate comes down here, and that's how we start this whole calculation. So minus x, plus x, plus x. Like that. So minus x plus x again. We have something on the right side, so even though it looks messier, because of the approximation holding, it'll be a simpler calculation. Yeah.
So how do you know you lost the 0.6
What's that?
for NaC2H3O2?
Yeah, right there.
Okay, so
Because this is a salt. This is a soluble salt, so it's going to break up 100% into ions.
so it doesn't have to be a strong base? Or
Nope. No, if it's a soluble salt, that sodium shows it's a salt, it's going to ionize 100%. And so that's the trick that we're using here. So that's whatever the salt concentration is, then the one, in this case, the anion, the polyatomic anion becomes 0.6. Same thing. We'll do out some more. This is just to give us an idea. And then on Monday, we'll start with, I didn't do the pH of salt solutions, partly because I forgot, and then as I was thinking, it's actually fairly complex, so we'll just do a simple one here. And then we'll do the more difficult problems next time. Okay, so if we do out our expression, we have here, we have 1.7 times 10 to the minus 5. This divided by that, approximation holds, definitely here. So 1.7 times 10 to the minus 5 times 0.4 divided by 0.6. So X, which is the concentration of H3O plus, is 1.13 times 10 to the minus 5 molar. So the pH, made the negative log of that. And this is going to be 4.95. Acetic acid on its own is going to be, at that concentration, would probably be in the 2 range. But you got to remember, now we're dealing with this thing that is the base. So you have an acid and its conjugate base. The base is now shifting away from this. So this is making it more acidic. This is making it less acidic. So it does get to be a little bit higher in pH because of that common ion. So we'll actually do the salts, and then we'll come back to this and do the buffer starting on Monday. But I think that's enough. I just wanted to touch on that before we... So 16 is pretty extensive. We'll get done with 16, and then we'll have 17. I don't know how long that'll take, but any extra time we have on the Monday before the exam, our exam is the Wednesday before spring break, I'll do a review of the tougher problems. So these are the types that we're going to be seeing. All right, so if you're set... you can go. If you want to see the calculations here, just take a little break here, let people clear out, and ask any questions. Make sure you turn in your lab from last time. And then we'll do these calculations here. Yeah, thanks. All right. Oh, yeah, look at that. Right. All right.
You got one more lap.
Is it?
My.
All right. Alrighty. Alright, so I'm just going to use my numbers. I made them up more or less. But based off of what I saw students were bringing up, there's a lot of differences. And the reason is because these are highly sensitive reactions. So just slight differences in the concentrations on the different tables. And just a few drops different can make a big difference in the results. But normally the results, no matter how different they may appear, they come out pretty well. Okay, so let's do, let me write up my values. All right, so I'm just doing them out as if they're the average. So you'll have to average yours, whatever it says to do. But let me just show you. And I'm just going to do it for flask A. So if it says use the average, then you'll just have to do two of them here. Well, let's do. First thing is we have the initial concentration. We're going to take that to be 0.1. Make sure that's true. Yeah, because that's the point. That's the Ki that was in the mix. So, and then room temperature. The temperature is just to ensure that if two students had wildly different answers, could see if there's any difference in the temperature, because temperature can have a big effect. So that's not as important here. Okay, so for flask A,
So the initial, is that for everyone?
yeah, everyone can use the 0.1. Yeah. So that goes into solution, then it changes into, some of it changes into I3 minus, but we'll see that later. So this is the final volume for me, initial, and this is for H1. You have two of them, I'm just going to do one. So wherever it says to average, that's what you want to do. And then the volume used. Okay. And then, make sure I have room here. And then for the first water or aqueous layer, initial volume, and volume used. So I have to write that out so you have it written down there. I think you know. Okay, so final initial. So if you started out with 0, then you should have 10 mils here. So 10 is what I used. This is 3. Generally, for the water, it's going to be less than it was for the hexane layer for the same flask. All right, so these are my values. And however, I had you average them and do them out. But okay, so here's what we do. So we need to. So you titrated with. Let me get the reaction. So you titrated with the thiocyanate. So sodium thiocyanate. I'm sorry, that's why I keep saying it wrong. It's sodium thiosulfate. Oh, that didn't sound right. The sodium thiocyanate was from this morning's lab for 1170. Everyone was asking where it was. Okay. And we need, where is it here? Okay. So this is going to break up into 2 sodiums and the thiosulfate ion. And that's the reaction that we're interested in. And where's my calculations? Right. Okay. And yeah. So this is the reaction. 2 thiosulfates plus iodine goes to 2 iodine, and then S4O6 2 minus. If it reacts with the triiodide, strangely, it it's still 2 to 1. This time there's 3 iodides and S4O6. So this one takes place in the hexane, and both of these take place in the water. But hexane is polar, so iodine is the only thing you find in there. Okay, so that's the reaction that we need. And what we're after, just make sure we got everything here, I2 plus iodide produces the triiodide ion, as I drew before on the board. So, but this is what we're after, is aqueous. How do I do it again? Aqueous. And so we want to find each of these things for the water layer. So why are we worrying about the hexane layer? Because both of these are going on in the water layer at the same time. So we can't distinguish between them. But there is a connection between the hexane and the water layer for iodine. And that is given as at equilibrium, that's why you did all the stirring. At equilibrium, the iodine that's in the hexane is equal to 34 times the concentration of iodine in water. Let me just write that as BQ. Okay, so that's everything we need. So we'll come back, we'll reference these things in turn. Okay, so we've reacted, the sodium thiosulfate that was in the burette reacted with these, and you did your titration. All the color was gone because these have the iodine has color to it, and then once the reaction is done, iodide has no color. So that's, you watch the color fade away. All right, so here's what we use. All right, so I'm going to take 1 moles of the thiosulfate as equal to this is the volume of the thiosulfate solution, and that's here. So you're using your volume. Mine was 10, and everybody uses this. This is the concentration of the thiosulfate. So everyone has a second term, but everyone will have some different volume for that. And I come up with 2.00 times 10 to the minus 4 moles of the thiosulfate. And this is for the hexane layer. Okay, now in the hexane layer, all that's present is the iodine. That's all that's in there. So we only have to, all you did when you did the hexane layer is you titrated the iodine. You only did this step. So there's no problem here. If you, whatever was used up here went into reacting this, so we have a straightforward calculation to do. Okay, so then you take the amount that you got there, and then you look at the reaction. 2 moles of the thiosulfate reacted with 1 mole of the iodine. So very nice and simple. Essentially, you just take that and divide by 2. Okay?
So I have a question.
Yeah.
Where did you get the 0.0100?
That's my volume in liters. You have to change the liters. So whatever your volume was that you got for your hexane, change that to divide by 1,000. So that'll go here, and then everybody has this. That's the concentration of the solution that went into your burette.
So we all have that same.
Yeah, but everyone's most likely going to have something different here. Okay. And then once you know your number, you're just essentially multiplying it by, or dividing by 2. And then the iodine in the hexane layer is equal to, for mine, is what we get above here. And then divided by the volume that you started with. What was the volume of the hexane layer that you transferred into the flask? In your pipette, what was the size of the pipette? 3. So you have to change that to liters, so that's going to be 0.003. So everyone will have that for the bottom. You'll have a different number there. And I came up with 0.033 molar. So that's the concentration of the iodine in hexane, which doesn't seem very useful because the iodine in hexane concentration is not here. But we're going to see that it's useful. So looking at this, if we know the iodine concentration is hexane at equilibrium, we know the iodine concentration in water, which is going to become important. So what we can say is that using this equation, the concentration of iodine in water is equal to the concentration of iodine in hexane divided by 34. So it seems like we're making things tougher than they need to be, but this is the only way to solve this problem. Once we get to the water layer, you'll see why, and this comes up to be 9.80 times 10 to the minus 4 molar. The box around this because we now have that term done. So we have one of the 3 things that we need to solve for case C. Okay? So that was the this is the titrating the hexane layer. So titrating the water layer. Okay, and so this contains I2 and I3 minus. Not much of this makes it into the hexane because it's an ion, and the non-polar hexane doesn't want this, but the polar water doesn't mind either of these. It doesn't have as much iodine. You can see it has 34 times less, but it still has it in there. Okay, so we do this out the same way. I use now my second volume. This is for the water layer, so I'm using 3 mils. And whatever you got. Some people even had less than that. Sometimes that happens. But if you have less than, remember, 3 mils is now 0.00. We're not used to, normally we end up with like 0.03 liters, but we have to make sure you divide by 1,000. And this is going to be 6.00 times 10 to the minus 5 moles of the thiosulfate. Okay, so here's the problem. In the water layer, we're titrating both of these at the same time. So, and they work the same exact way. 2 of these for 1 of these. They produce more iodide, but we can't tell anything about that. So there's a certain amount of iodine and triiodide in the water layer. How much? Is it 50-50, 10-90, 1%, 99%? We don't know. But we do know both of them are in there. So what we have here is a problem. We can say that the moles of the iodine, actually let's look down here. So we can say that we take 6.00 times 10 to the minus 5 moles of S2O3. And then we have to do some really unusual thing. We have to say 1 mole, 2 moles of the S2, the thiosulfate ion, will react with 1 mole of iodine and triiodide together. How much of each? We don't know. It's not 1 mole of this and 1 mole of this. It's 1 mole total. So this says that we have, what do we get? 3.00 times 10 to the minus 5 moles of so there's 3 times 10 to the minus 5 moles of iodine and triiodide together. We don't know how much of each. So that's the problem. It's all mixed in there together. The reaction worked the same way. So we have a mixture this time. And we don't know how much of each we have. But we can also go on to say, and this is where you give that bar where you have to do the average. So you got 2 of these to do. So you'll have to average them, but they both work the same way. So I'll trust that you can do that. If not, after I get done here, we can go through it. But you just have double the stuff to do. And then the volume is the same. You took it from the water layer. It contained these 2 things. So you end up with 0.00 times. So the concentration of the iodine plus the concentration of the triiodide is this. But we have no idea which one is more or less, or if they're equal. We don't know. So if that was it, we'd just say, well, there we are, we're done, and we couldn't find Kc. We'd have to stop. But what we need to know, we know this number. Essentially what we have is 2 variables. Is there any way, is there anything that we've done to allow us to know one of these? Looking back over here. Here's the trick. We did the hexane layer because we knew that there's a relationship between them. By finding the hexane one, because it was just iodine, very simple to find, but we backed out the iodine for the aqueous, we're guaranteed that the iodine that's in the water layer is 34 times less than the hexane. So we know this one. So we know this. So we got that going for us. So if we know that, then we can say that the triiodide is equal to 1.00 times 10 to the minus 2 molar. I haven't even been paying attention to make sure. Minus 9.8 times 10 to the minus 4 molar. So I took this value and put it here. And that's what you'll do. So we did the hexane layer specifically so that we could back out this. We did this one with these together adding up to this, but we don't know how much is which. So now I've just put in actually, let me write the whole thing out here. So it's going to be 1.00 times 10 to the minus 2 molar minus, so you don't wonder where that number came from. This one we got from over here, so this is 1.00 times 10 to the minus 2 molar minus what I have there. So a little trick, a little neat thing, so they're going to actually solve this. I came across this one when I was writing up the labs, and I thought it was the slickest thing. It's like, wow, that's, I've never seen it before. There's a lot of these chemical reactions out there that it's fairly standard. I just had never come across it before. So it's neat that we can, we'd be stuck, except we have the hexane layer, and we know this equilibrium. This value here allows us to find this in another way, and we plug it in, and then we can find the triiodide, wherever it is. Right. So 9.02 times 10 to the minus 3. So now we have this one. Now all we have to do is find the iodide. We know it started at 0.1. What we also know is that any triiodide, there was no triiodide to start, so any that came into existence here came from here. It's 1 to 1. So the concentration of the iodide in water is going to be equal to the I initial minus the concentration of the triiodide. Because any triiodide that's in here, this stuff, all came from the iodide, from the I minus. So we just do the calculation. Everybody has 0.1. You take your value, that goes in here. So this is 9.02. And I get for mine 9.0 times 10 to the minus 2. And now we have the triiodide, or the iodide. We have the last term. So everything that's in a box is one of the terms for Kc. Now I'll go back through it real quick here, but let me just finish up. So the Kc value then, I'm going to put it somewhere, so it's here. So Kc is equal to the triiodide over, and this is all aqueous, the iodine and the iodide at equilibrium. So this comes up to be 9.02 times 10 to the minus 3, 9.8 times 10 to the minus 4, and 9.10 times 10 to the minus 2. And for mine, it came out to be 101. Low hundreds is what we normally see. But if you get in the thousands, you get, and you should, because the equilibrium constant is independent of what was in there. Both your K values for the flask A and flask B should be the same. That was a point of the experiment, one of the points of the experiment. Your K value should be independent of how much you put in there. So sometimes people get really good results. Sometimes they get one that's like, I think the real value is in the low 200s, the actual tabulated value. But whatever you get is what you get. I get people that get like 235 and they'll get 1200. So that's okay. You don't get marked down for that. I just want to make sure you got the math right.
Professor, quick question.
Mm-hmm.
That 34.0, we all have the same one?
Yeah, that's just showing that the concentration of iodine and hexane is 34 times higher than it is for water. So that 34 is a constant at room temperature.
So when we do like, we do one for flask A and for flask B, but we don't do like H1 and H2 separate, we just take the average of
Yeah, I
concentration
think, however, it said to do the average. I don't know if you do the average before all of this or after, whatever it says to do. Yeah. And actually, it doesn't matter which way you do the average, either before or after. Yeah.
For when we did the water, is it for the leak? No, that one.
Oh.
Yeah, so that first number that you got, the 0.003 liters, that's yours?
Yeah, that was mine. Yeah, so whatever you had for that one. Yeah.
Is that the same for the hexane layer, the 0.003 liters?
Yeah, that one is.
Yeah, this one is the volume that we use. So that one.
So that one is the same.
Yeah, unfortunately, I'm sorry. I used the same. I picked a number that's exactly the same as this one. Sorry, but yeah, it's just they happen to be the same. But this value here and this value here are supposed to be 3. Yeah.
Where did you get the 0.100 and the bottom? Where you subtracted?
Here.
Yeah.
This is everyone has this. This is the starting point of the iodide is 0.1. That's what it said on the bottle. And then we must have used some of it to make the iodide, triiodide, so we subtract that out. So it doesn't make a huge difference, but a little bit. So you should be able to find KC for both flasks. And if they don't match up, that's fine. It's no big deal. But it's surprising how often that they do. Or at least one of your values will be very close to the true value. Which again, I don't know off the top of my head, but it's something like low 200s. But I don't grade you on that. I just want to make sure your math is correct. The good numbers usually fall out.
Good luck with today's lesson.